everybody to this wonderful talk today. It's my great honor and pleasure to introduce Tim Januschowski, who is one of the smarter forecasters that I know. He started out at SAP, went on to Amazon, now ended up at Zalando, fashion retailer, online fashion retailer in Europe. He's going to talk to us about forecasting for pricing, and he already said he has enough material to talk for 2 hours, so let's see what comes out of that. I'll try to stop him at some point.
And let's also see if this is going to be a wonderful talk. But thank you for the kind introduction, Stefan. And me being here has a lot to do with Stefan. Of course, we were colleagues at SAP. I was trying to do some forecasting. And, then met Stefan and he sort of taught me how it's really done. Can everyone hear me okay? All right.
Can you speak up a little bit?
I will try.
Thank you.
Boy, there's places up front here in what they call the splash zone. All right, so I want to talk to you about forecasting for pricing, the challenges that we have there, and some of the sort of recent progress we have made in this area. This is not just my work. It's work with a talented bunch of folks that are listed here in one of the preprints, as well as my boss and a bunch of colleagues. So I want to acknowledge all of their contributions. Anything that that's right on the slides is theirs, and every mistake is probably mine. So we'll want to introduce Zalando to you a little bit. Zalando is a leading fashion online retailer in Europe. It's active in 25 European markets. We have a lot of brands, more than 6,000 brands available, 50 million active customers. We're selling mainly clothing, but also things like Lego. But it's really a clothing and apparel reseller. And what we have in the kind of problem that I want to spend time with you in the next hour or so is the following forecasting problem. We want to forecast the demand for all of these products that are available on Zalando. Zalando has a platform business and a wholesale business. I'm interested in the wholesale part of it. And we want to forecast demand 26 weeks into the future. That's the course of the season, typically in the fashion industry. And we want to do it in weekly granularity because that's how we change prices. A fun sort of twist here is that in the fashion industry, to a large degree, you have a fixed inventory assumption. So at the beginning of the season, somehow you get all this fashion apparel stuff, and you need to essentially price it out optimally. So pricing is in a sense an inventory control mechanism. There's a part where you can actually reorder during the season, or any of the boring stuff that Stefan and me wear that's not seasonal. You can reorder that, and then you're in a classical inventory, or supply chain or inventory inventory management scenario. But I'll be focusing here on the larger part where we have a fixed inventory at the beginning of the season, and then we have a pricing engine that takes demand forecast as one of the core ingredients into account, but it's by far not the only ingredient and not the only probabilistic, not the only model. So to make this maybe a bit more tangible, what we have, or my organization is responsible for, is to set, can we see my cursor? No? Here. We're setting the black price. This is the sort of undiscounted price. We're not going to talk about how we set this today. And then there's a discounted price, this one here. And that's the object of interest for today's talk. Europe, if you think about where Europe is leading in terms of innovation, there are many people say, much of the AI advance is happening in America and in China, but Europe is leading in regulation of AI. We're also leading in the regulation of price display. So this is a very highly regulated thing at this stage, and it can lead to artifacts such as the following here. So we have this bag, a backpack. We say we have it discounted, but now with the new regulations, we actually have to show it relative to the last lowest price, and we see a positive discount. That's an interesting sort of message, to pass. What I take away from this is that you need really a high degree of automation. If you have, or at least algorithmic control, because if you're driven by human intuition, you think today is the day that we'll do a flash sale for this backpack. I'm going to turn the season around, or whatever goes through your head at this stage. You will have a large effect for a long time here, where you show this positive discount, and that might not be as cool. So that's a fun complication of the problem. One of the main things that I like to say is that forecasting is a means to an end, never its end, or in very selected cases only its end goal. And here, the end goal that we have is we want to set optimal discounts. So I want to familiarize yourselves and ourselves a little bit with the kind of optimization problem into which our forecast feeds into, and that is we want to maximize profit. That's this function here. It consists of two components: whatever is left at the end of the season, times the salvage value. You don't have to burn the inventory. You can also, send it to. Zalando has a lounge business, for example, where you can sort of offload bulk products. So this is essentially what's left over here, but you'll make less profit. And then essentially, what is the profit throughout the season that we're going to make? So this is not for the next week, but for the course of the entire season. That's the kind of optimization problem, and our demand forecast feeds into this problem. We have the decision variable is what is the discount that we're going to choose. It's a discrete variable in our case because we want to say it's 0, 5, 10, 15, 20% or something like this. And then essentially this is another decision variable. I'll explain that a little bit, that is bounded by the demand. So we can choose to fulfill less demand essentially. The profit function itself, also want to mention that itself, came across a little bit innocently here with this pi, but it is a complicated function itself, which in turn contains model input. This here is the return rate forecast. So in the fashion industry, a lot of people try things on, then send it back. Sometimes they order smoking, get married, send the smoking back. So there is a bit of a problem here with the return rates. And you need to estimate this as well. But once stuff returns, you can resell it, right? So you can it goes back into your stock. So there's a bunch of complicated components here. We have a bunch of constraints as well. We can only ever sell as much as we have stock. That's the first constraint. We want to set exactly one discount level. It's this constraint. Here we can choose to fulfill less demand than we could. This is this constraint here. And what is this constraint here? 5. And this is where the demand input comes into play, right? This is the core object of our interest. And if you've looked at this for some time, you will see the painful truth that unfortunately this is a point forecast and not yet a probabilistic forecast, but we're working on it. And these are not all the constraints. There's a bunch more. You want to not change discounts too much from one week to the next week. You've got some targets that you want to achieve. For example, a minimum amount of revenue, right? And typically by lowering prices, you make more revenue. And then you also have things like an overall discount rate, a sales-weighted discount rate here. This is this constraint that essentially ties all the ties the optimization problem. Yeah, well, you could think about that. You would optimize prices for a single product, but we also have some kind of metrics that tell us that the overall discount level should not exceed a certain amount, and this constraint here then expresses this fact that the discount level is within a certain corridor, and then that complicates the pricing problem, the pricing optimization problem quite a bit. Right. Let's look at the data that we have here at our hands. It's a typical long tail distribution that you see in practice so often. We have lots of products here on the left that don't sell at all, or very that sell very not so much, and then there's a long tail of potentially high selling products. In total, there's 500 products, 500,000 products, but they exist in different sizes. We only look at the overall product and not divided by size. We have 25 marketplaces, and so there's a lot of time series that we have to forecast. The covariates that we have available include things like catalog data. Is this a T-shirt? Which brand is it? Importantly, did we run a promotion? What is the price level? And the in-stock levels. What we're not using that might be also interesting is weather data. My business counterparts, they always, make me aware of that fact, but we're not using it. We also don't use any funky image embeddings or text embeddings. And let's look at a couple of time series that we have here, a couple of real-world products. The red dashed line is the discount level. Yeah. Blue is the demand of the item before returns, DIBR, and green is what we predicted it to be. So for this case, if you're looking at it carefully, maybe there's a correlation between discount increases and demand goes up, but it's subtle. In fashion, you run out of stock quite a bit, so that's a problem that we'll ignore here, but it's something that is very important in practice. And we have the stock level here, right? So there's a very concentrated period on the life cycle of the product where we are actually in stock. This is where all the magic happens, and then we are out of stock for most of the time. And this is a real product. We also have short histories. I didn't talk about the fact what is the history available at forecast time. So this here is when we start to forecast. Everything to the left is what we have available as history. So basically we have to hallucinate the demand out of thin air for this particular product. Right? But that's quite a common scenario, especially at the beginning of a season. So we don't start forecasting right at the beginning, but typically 4 weeks into it. We have sparsity, all the kind of complications that you would imagine, right? So if you look at the y-axis here now, this is a very slow-moving product that a lot of the times doesn't sell at all, even though we change the price quite a bit. And then to go over the history of demand forecasting between just before 2018, so it's a long time before I joined. I'm with the company about 18 months. The company was doing a classical combination of time series models, ARIMA, and then you discover a corner case where ARIMA doesn't work, so you build something around it, and you build up this complex pipeline of models, which then at some stage puts you in a box where you're not making any progress. Then from 2018 to 2020, folks started experimenting with deep learning models, and essentially it is eventually settled on transformer-based models. I'll talk about this a little bit. And since I joined, the kind of focus I try to put into the team is, let's look at the causal relationship between price and demand. That seems to be a key key thing that we need to control here in this application, and probabilistic forecast as well. The journey is not super particular to Zalando. If there's a very interesting blog post on the history of Amazon's demand forecasting system for inventory management, and I would encourage you to check it out. And the kind of optimization problem that I went over, there's also preprint available. Right, if we compare our data to the data that is publicly available, for example, the M5 data. I'm taking the M5 data because that's probably the most meaningful data set that we have publicly available. So we have weekly data, M5 is daily. M5 is of a very limited size, but still sizable enough. We have a very big data set, but most importantly is the kind of price changes that we see. Walmart has an everyday lowest price policy, so you hardly see any price changes. This is the distinct number of prices per item, right? So most of the items, or many of the items, they hardly change price over the course of the lifetime of the product. That's that's the Walmart pricing strategy. They're well known for it. On the other hand, what we do in fashion is to change prices quite frequently, right? So in that sense, the Walmart data set is not very meaningful, unfortunately, for this kind of pricing challenge that we have at Zalando. And then what is the object of interest that we want to produce in the demand forecasting problem? It's essentially a demand discount grid, right? So we have our discrete discount levels here on the x-axis, and for every discount level, we have to produce a demand point, right? So this is per forecast horizon, right? And of course, ideally, this wouldn't be a matrix, but a tensor where there's a third dimension where we have actually the probability distribution per discount level. One of the reasonable assumptions that people make in econometrics is that this demand grid, or if you interpolated this curve here, this red curve, is monotone, right? If you increase your discounts, you will not sell less, essentially. And controlling this kind of relationship between discount and demand is something that is crucial for solving this problem well. And just to recall, the price was given to us or is available to us as a covariate, but there are other covariates that we have. Just want to go over this. So some covariates, they influence our forecast, but we only observe them. Day of the week or holiday. We can try to change it, but it won't happen. We have covariates that influence our forecast, and we can intervene on them. What's a promotion? We can decide to increase our marketing spend. We can decide to reduce our prices. And what we typically want is we want to have a good estimation of the causal effect of price on demand, but we also want to predict well. We also want to sort of fill this discount grid in a somewhat most accurate way. So we're in the intersection here of causal inference and prediction. Then these interventions here that can be continuous or discrete, right? You can make a choice. You could potentially make a continuous intervention on price where you just change the price, a little bit. But here, we do it we do a discrete intervention because we say we change the discounts only in steps of 10%. All right. So, yes.
Would you consider the click data in the model?
Yeah, we could, and especially at the beginning of the season, that's important. but then you don't have click data in the prediction horizon. So either you do a sequence-to-sequence approach where you say we don't have that in the prediction horizon, or you do a multivariate model where you also predict the click thing. But it's something, yeah, it's a good one. I would include marketing spend first before I go to clicks. So where are we here in this presentation? Hopefully, you have some understanding of the data and the kind of forecasting problem that we have. And assuming we have this now fixed, one of the big questions is how do we evaluate our forecasts at all? On what do we evaluate it? What kind of data sets do we have for this? And then what is the accuracy metric? And then this will be fairly hand-wavy. I'll talk a little bit about this, and then we'll go to the modeling part. But let's talk first about evaluation. And evaluation in this causal forecasting scenario is hard, right? Because we have this, we have to answer this counterfactual question. For a price discount level that we never observed, what would the price have been? So what the best thing would be is, the ideal scenario would be we can do price randomization. And there's a lot of successful companies out there that do price randomization, and it's the DNA of them. If you think about Uber, Lyft, Booking, those companies, they change prices all the time. So they get a very, very good handle on the price elasticity. At companies like Amazon or Zalando, they don't really want to discriminate prices by customer. It's a strategic decision that sort of pains the scientist, but I can totally understand it, right? If it just doesn't generate a lot of nice press. But you could still try to randomize prices at least over time, right? So not by customer, but over time. But every time I, talk to my, business counterparts and I mention the word, let's randomize our prices, they don't show the reaction. They don't share my enthusiasm on that kind of context. So let's just assume that this price randomization, unfortunately, is not possible. So what else could we do? We could just generate data, synthetic data, where we control everything, especially the intervention, and then build our model around that. And we're running actually competition, or we were running a competition with the American Society for Causal Inference, where we created what we believed somewhat realistic synthetic data set, and then we could produce the demand grid for every data point as well. But that, of course, it's nice for model building, but would it convince a business stakeholder that you've actually made some progress? Probably not. So the next best thing that you can do is to look at natural experiment data. So and I'll talk a little bit about this later. Sometimes our competitors change prices, and then we choose to follow them. We choose to match their prices, and then there's a sort of policy break because we follow their prices, or we don't follow their prices, and then we have this kind of off-policy scenario. Sometimes we do A/B tests, or we do A/B tests quite a bit with our prices, and then we have a natural way where we have separate groups of prices. What can also happen, is we deploy a bug, and some prices go really bananas, and then we have a wonderful off-policy data point. But again, enthusiasm around this is not always shared. But yeah, natural experiments can be a second one, or we can take advantage of special weeks. And in e-commerce, especially the kind of cyber week is very important. I've roughly marked it here in yellow. What we're seeing is, the cyber weeks. I think this is demand, aggregated demand. It's discount levels with the standard deviation, yearly discount, average discount levels. So you can see Zalando's discounting more over time. And And you can see that the discount levels in the yellow areas here are, especially relative to the year before, they're different, right? So there's more discounts happening in Cyber Week than during typical regions of the year. So you could use the Cyber Week as a week where you have an off-policy event, and you can try to evaluate your models on those off-policy weeks in particular to get a better understanding of how well have you captured the causal effect. And here just another view that Cyber Week really is different. So on the left-hand side we have the average or the discount levels in Cyber Week. So we see that we have a fair amount of high discounts. And in a regular week, right, we don't discount as much. So it really is a different week. And one way what we could do is to build up a kind of experiment where we have in our training set, we have two kinds of training sets. One of them is one that includes Cyber Week, and then we evaluate on Cyber Week. That's what we could call as our on-policy in-sample training. And then we could also see, like, if we take Cyber Weeks out and just paste in a random week, and then only evaluate on Cyber Week how well do our models extrapolate to this kind of scenario, so that we get a better notion of out-of-policy testing. Okay, so now we have, and of course we can just take our regular data sets, right? We don't need to necessarily worry about, off and on policy. We could just say, okay, we just do a regular forecasting backtest. And that, of course, is an option. Now, then the question is, if you have your backtest data set under control, what kind of forecasting accuracy metric are you going to use to tell you whether forecast A is better than forecast B? And ideally, of course, you have a forecasting accuracy that correlates well with your decision problem, and then one thing that you can do is you just choose a standard forecast accuracy metric, on the right data set. I'll mention a couple of custom built accuracy metrics that correlate a little bit better with our decision problem, or what you could do is to take a variant essentially of the how do I call this? It's a variant of quantile losses essentially for this causal scenario. You compare your actuals with your forecast with some kind of accuracy metric, and then you weigh this by the inverse propensity. So if you're unlikely to have seen the price in the past, you overweight that training sample because it gives you a disproportionate amount of information. This is what this inverse propensity score, could give you. You can also use this function here as a loss function in your favorite neural network architecture. We're not there yet. This is something that we want to try out that I think makes a lot of sense. But then, of course, you need to have a model also that estimates this propensity. Yeah.
So can't you, like this G that you have, like you do some sort of evaluation on the demand and then you put it for your decision-making part? Can't you also like kind of put this G as a parameter? I mean, there is all this end-to-end demand and allocation problems people solve. You said that for this GI, you can assume it's some sort of whatever mean square error or whatever you could use. But then you have a loss function for your decision, but for your demand, you have something else. But can't you just have basically end-to-end where you end up just having one bigger loss function to solve?
In theory, yes. In practice, very hard, right? We talk about at the kind of problem size that we're looking at. Just training the forecasting model takes like three days. And then the optimization problem also takes quite some time. You can't really backpropagate the loss through because we have a MIP, mixed integer program. ideally, ideally you would say this is a causal reinforcement learning problem, but yeah, I think maybe in 5 years I'll be back and I'll talk about this. Right now it's a bit far-fetched, but conceptually you're exactly right. And there's a bunch of inefficiency we introduce by decomposing the problem as is. Yeah, that's also out of question. All right. So hopefully now we have some handle on how do we evaluate our forecasting approaches. We know what the forecasting problem is and what the data looks like a little bit. So now let's talk a little bit about models. So what kind of forecasting model are we going to throw at this problem? And there's the ladder of causality by Judea Pearl that gives you sort of varying degrees of how well do you handle with this causal aspect. And I'll try to sort of give you a model on every stage of this causal of this ladder of causality, and we'll start by simple incorporating structural assumptions, essentially making this association only. For the intervention part, I'm not sure if this is a one-to-one match, but you can think about combinations of models from econometrics and predictive models, and if Stefan shows me the sign, I might skip over this here, but I do want to sort of go over this double ML inspired work that's sort of coming out any minute, hopefully, or that we're submitting any minute. Okay, so the most straightforward approach that you can do in forecasting is, for this kind of problem, is you have your forecast that you want to produce, a probabilistic forecast, and you conditioned it on your past, right, on the past demand that you've seen, as well as covariates, right? And these covariates, in our case, would be price. And the covariates here, we have a capital T, so we go from, we also have the covariates, the price level available in the future. If we don't have that, we can just set it ourselves. And most sort of standard neural network models that incorporate covariates, you can just use that, and that's the most straightforward thing you can do. However, if you do that, we talked about this monotonicity, between discount and demand. All bets are off. It's neural networks anyway, but you completely. There's no guarantee essentially that your demand will monotonically follow the discount level. Okay, so the straightforward approach may be a little bit simplistic. What you can do next is to encode this kind of structural assumption that you're making on the monotonicity, and you can encode this into your neural network by saying that your demand is a stepwise linear function that increases, that has positive slopes. This is essentially what this equation here says, and then all the kind of free parameters that you're estimating. So the slope, in particular, the output of neural networks. Right? And you can encode this very easily in a neural network, and then you guarantee, and you can do that by using simple things like a soft plus to guarantee that your slope is positive, and then you end up with a monotonic function, and you have captured this additional information of this monotonicity, and you can plug it into a standard transformer architecture, or standard in air quotes. So we have, it's non-standard because we have essentially in the decoder of our models, we have two separate decoders. One that considers the short-term horizon. This is because we want to be really good for the first couple of weeks. We always make a decision on the price for the next week plus the long-term profit. So the first week or first couple of weeks are really important. So we have a special decoder just dedicated for the short-term horizon, and then there's another one dedicated at the for the longer term horizon. And in much of our training, we actually focus here on this one. So in the first few epochs of our training, we essentially only updates the weights here of the short-term decoder, leave the weights of the long-term horizon decoder fixed, and then only at the end of the training do we actually, do something here. The part here on the left is standard transformer forecasting transformer methodology, and then second non-standard thing is that we have is this monotonic demand layer, which is essentially this encoding of the piecewise linear function. All right. And then the output of our neural network is essentially this forecast discount demand grid. In practice, we have around 75 million trainable parameters. So it sounds maybe a lot, but if you compare it to what ChatGPT has, it's small. But you still need like a couple of days of training.
And how often do you retrain it? Like, probably you have, very high frequency data, like daily, hourly. But I don't know how long is your horizon. How often do you need to retrain?
So we have a 26-week horizon. We have weekly data, and we retrain from scratch every week. And that's of course not necessary, right? You can take your last model, don't even retrain. It does, it does improve accuracy if you retrain, but you could also warm start. But we don't do that. Okay, so then the question is, does this work, right? So here we've taken a demand data set from Germany, a subset, so a smaller data set of what we have. We compare it to a bunch of baselines. Naive forecaster, always a great baseline, Light GBM, Deep AR, something I worked on in the past, and especially the Deep AR column. I think take it with a grain of salt. We didn't really optimize this quite a bit, but yeah, this is a table, where in your paper where you want the bold numbers to be at the right places, they are at the right places, so we are happy. Now, this is a small subset, and one of the interesting experiments, or one of the questions we wanted to ask is wanted to answer is, we have this highly parameterized transformer, is it worth it? And how do we justify this? And typically, if you look at the literature on transformers and NLP, one of the more interesting results is that transformers are, they adhere to some kind of scaling laws. So if you throw more data at the thing, right, the accuracy improves quite a bit, and that's something that we try it out here as well. So we have a fixed size model. I'm not sure if it's quite 57 million. And what we increase, this is here on the x-axis, we increase the size of the training set. Right. This is a log. This is log plot. And here on the y-axis we have the accuracy. The size of the training set increases. The test set stays the same, right? These are two separate sets, no overlap. And then we have some local forecasting baselines here, right? So, if you don't change the test set, the accuracy will stay constant, right? I don't know exactly which baselines these are, but the fact that it's a horizontal line, makes sense if you're talking about a local model that you have one model per time series. And then we looked at, what do our transformers do, right? First, there's a regime here where they're actually not better than the local models. Then there's this phase where, they're sometimes better, and then there's a regime here somewhere after the sort of around the size of the Germany data set that we use, where the accuracy just gets better and better. And yeah, this horizontal line, I don't know what that is. We'll have to figure that out still, but accuracy improves, and this is a log plot, right? So it's pretty cool. And then of course I said to the team, let's just use all the data we have and see what happens. And then we have forecast GPT or something, but yeah, we haven't managed to do that unfortunately yet. The important caveat maybe for you is if you're using transformers in your forecasting practice or research, I think you do need the right data for it, right? The kind of data that I showed you is essentially not infinitely large, but is very, very large, especially if you go back in history. And we seem to have some kind of regularity or conformity in the data set as well. And many data sets, especially ones in publicly available, they're not like that. Here's a plot from a work that we did when I was still at Amazon. Is essentially, over all the public data sets, publicly available data sets, we sort of ordered them by size. Where's my cursor? Here, right? And then the blue dot is always the best method best accuracy of a method that we had in our benchmark set. And one of the methods there was the TFT model, by the Google folks, and this here clearly is not a scaling law. So on publicly available data, we couldn't, we didn't find any evidence for a scaling law as we had seen for the Zalando data. Right, and now you're wondering, like, there's so many papers on transformers. Some of them are on the esoteric side. So whenever I read a paper that says long-term something, I always wonder, okay, why do they have to go that way when they're able to show it for the core task or interoperability or something like this? There's mixed evidence in the sort of literature, on the publicly available literature. However, we have evidence from big industrial labs, Amazon demand forecasting teams, as well as Zalando, where there is evidence of transformers in production. And despite of what you may read on LinkedIn, these companies, they're betting serious money on this. Okay, but it is, in my opinion, it is a function of the data. So if you have a lot of data, it's sort of, related. The things are related. Then transformers will be successful. But if you were in my workshop on Sunday, there was a presenter, Kashif Razul, who's working also for Hugging Face, and he's building a foundational time series model. You guys are also doing that. So this statement that I just made may not age too well. But for the moment, that's my opinion. All right, so we have essentially, I've hopefully shown you a model where we incorporated structural assumptions into our model, into our forecasting model, but there was really at no stage any kind of notion of causality. So let's try to bring in this notion of causality a little bit. And despite what Judea Pearl says, maybe causality is a topic that has been an active research topic before he started working on it, and in econometrics. And one of the things that econometricians ask themselves is, what is the price demand response function, the price elasticity? And a very standard approach is to use a two-way fixed effect model. Two-way fixed effect model is just a funky name for a Poisson regression with specifically chosen covariates. The specifically chosen covariates are here UIs. That's some kind of article effects, right? These are just indicator variables. And then these one here are day of the week are sort of time features. So you include this in your regression, and then an econometrician will try to convince you that you've taken out all the confounding effects, and then the only thing that remains is the effect of price. And then you can try to estimate this effect of the price, and the effect will be a causal effect, right? This is this epsilon. The epsilon is the price elasticity. So how much does changing the price, how strongly does this influence our demand, right? And this, you want to do this in the log domain, because typically you expect a multiplicative effect here, all right? And then one thing that you can do is, so you have this price elasticity two-way fixed effect model. A model is giving you some kind of price elasticity, but we also have this transformer model, right? The one that I've shown you with the piecewise linear function, and then you can try to compare those two elasticities. And well, one of the problems is you don't have a ground truth, but you can at least look at if they're different or how much they're different, and they seem to at least agree directionally. But the kind of the elasticities that we observe in the transformer model, they're in general a little bit lower. Okay, but now let's say we have elasticities estimated by our econ folks, and then how would we use those elasticities to actually forecast better? Because we're really interested in getting the causal effect right is one thing, but we're really interested also in this prediction part. And then what we can do is to say we take our exponential smoothing approach, where our forecast YT hat is just a combination of what we've seen in the past, right? And we weigh this by the price change power to the power of the price elasticities that our two-way fixed effect model has given us. So that's a very, very simple approach how to sort of combine a classical forecasting model with an econ model, right? And of course you don't have to use exponential smoothing here. You can also plug in a different model. Right. So this combination of econ and ML approaches, one way that I've shown you just now is to take decouple those questions, learn or causally infer the price elasticity, and then combine it with a forecasting model. There's other ways you can do this. For example, you could use the price elasticities to augment your time series, your training time series. Right, you induce a couple of price changes, use the price elasticities from your two-way fixed effect model to produce a new augmented time series. That seems to be working much less well than I was hoping, but still sort of somewhat working. And then the third approach that we haven't tried is to actually, just directly input this, use the two-way fixed effect model inside the transformer as non-learnable weights. Or you regularize towards them, right? Okay, so this is basically a combination of causal and econ models. So didn't show you any accuracy numbers. In general, it sort of works for sales periods quite well. In the general setting, not as much, or not so convincingly. And then the last one, this is sort of the most speculative one. That I want to talk to you about is sort of a double ML inspired forecasting model that then sort of goes, is on the ladder of causality is the highest kind of model that we have that I wanted to talk to you about today. So what we have, if we look at the causal graph, is we have all kinds of confounders here, right? This could be past price or past demand, also day of the week or something that causally influences our discount. Also causally influences our demand. And then there's a causal influence between discount and demand. Now you may wonder, demand may actually also causally influence discount, right? You've not sold enough. I'm going to increase my discount. And I would answer, yeah, you're right, but all of this is here in X. And then what double ML does, double ML is a methodology to estimate the causal effect, the average treatment effect in a somewhat flexible way. So in structural equations that looks something like this, the outcome, Y here, in our case this is demand, right? This is an additive linear model, right? But you can, I'm choosing this here for simplicity of exposition. There are more complicated approaches available. So your demand depends on the elasticity so the effect of the treatment, and the treatment is the discount level that we're setting, plus some other stuff and noise, right? And then and this other stuff here is sort of the base demand. And then this the discount level in our case, or the treatment, depends on some on unobserved, and on the confounders. So this one's here, right? So that influences the treatment or the discount in our case. And again, we have some noise, and there are some, and we have learnable weights, W, and then there's some assumptions around the noise. But interestingly, there aren't a lot of assumptions on F or G, right? And this is maybe the magic of the double ML framework, is that you can use a neural network here and here, or a gradient boosted tree or whatever, and this causal inference methodology will still work. Okay. In fairness, we need two slides here to explain it. So we have one model that sort of gives you the residuals or this is what we're trying to estimate, sort of the treatment effect. And for this, we sort of need we need a model here that estimates how well we're able to forecast the discount itself, the propensity essentially, right? And if we have this, then we can try to identify the causal treatment effect, theta, simply as the minimum of this expression here. Right. And this is then, when we do this, we get this theta hat, and that should, in our case, then give us the causally correct price elasticity, right? Now we're not doing causal inference here; we're doing really forecasting. So in a sense, what we're doing is we try to take this approach, or try to take these three models essentially that we have. And then we forecast with them. We try to forecast with them as well as possible. So the causal inference aspect, essentially, we ignore it, or we take it as inspiration and hope that it improves our forecast accuracy in specific situations. Right. So what we have essentially are three models. We have one model that gives us the future discount. We have one model that gives us the future demand, and then an effect model that gives us that combines the future demand with the forecast discount to get us the actual demand. Right? Those two models, they are called nuisance models, typically in the literature, and the model then that combines the two nuisance models called a final effect model. And in our case, all of these are transformer-based models, essentially the architecture that I showed you before, but with a modification of the output.
Yeah, I'm sorry, maybe I'm not entirely following, but I thought like the future price and the future discounts, you control them yourself, right? Or why would you need to forecast that?
Let me think about this. I'll come back to this at the end, okay? But it's a good question. The simple answer is because because the price also depends on, so you really care about the sort of, or you should care about the sort of real price changes that are different from what you had before, and that are sort of, no, that's too hand wavy. Okay, I'll think about it. Sorry. Okay. Anyway, so let's assume that we have all these machinery together. We have three models: nuisance models, final effect models. The final effect model here is essentially again our price elasticity. The price elasticity is output of a neural network, and this is how we compute the demand. And then how do we test this? How do we test this? How could we evaluate this if it really makes a difference? And let's go back to this kind of setup that we had before, where we have an in-policy training. We always evaluate on Cyber Week. We have one setup where we have Cyber Week as part of the training set, and then there's a second setup where we do not have Cyber Week as part of the training set, and then try to see if we're able to forecast during Cyber Week well. All right, and here's some results. We took as our Remax as a local baseline, just to for plausibility reasons, so that we say that okay, our actual models they're doing better, and this is the case. And what we see here in the in-sample column is essentially that if we don't take this double ML approach, if we just take the baseline model that I showed you at the beginning, then we're very good. Essentially, according to most of the metrics, this demand error is an MSE where we're weighted by the price. So because we want to be better at the higher priced items. So that's okay. That's something what we would expect. And then if you take the Cyber Week out of your training examples, but you still evaluate on Cyber Week, then you can really see the effect of the double ML method, where you're making much better forecasts. Right. So that was one experiment that we looked at, and the second experiment was that Zalando sort of typically matches competitor prices, but not always. So we constantly run A/B tests where we stop to match competitor prices, and whenever we stop to match competitor prices, there's sort of a break in the policy. So this is an off policy kind of situation, and we could try to evaluate on this. Right, and this is an example here. We have with treatment and control groups. Here we match our competitor prices. Here in the red line, we continue to match our competitor prices. And in the blue line, this one here was a selected group where we decided not to match our competitor prices. And then the mean discount level drops by quite a bit. Right? And then this is here the week on which we want to evaluate it, our forecast models, because this represents our sort of off-policy scenario. And then we have the same experiment as before, where on this off-policy experiment, and this is mean absolute error, where the double ML inspired approach works best. And then we compare it against the transformer model also. But it is important to say that this is not the kind of transformer model that I showed you before, but one that is artificially inhibited, in the sense that we don't train it on all the data, because we wanted to make sure that this kind of non-causal transformer hasn't seen any off-policy data sets. So this column here, you need to take it with an extreme amount of salt. And in fact, the production model, the model that has seen all of the off-policy effects, will turn out to be much better than all of these three columns. All right, and with this, we're at the tough questions part, essentially. Do we ever, in such a big data scenario, do we actually ever have an off-policy regime, right? Especially if we're thinking about global forecasting models that have seen essentially all kinds of price discount levels over all kinds of products in the past. Is there ever an off-policy scenario that we have to sort of insure ourselves against, right? And the experiments I showed you, they're interesting academic exercises maybe, but I'm not sure how convincing they are, right? And then there's this question about like what is more important? Is it the causal inference part or is it the prediction part? Right? If you ask this audience, probably you would say prediction is the most important part, but economists would probably disagree. And it's also very unclear which of the effects is more important to get to have under control. What is the harder one? And can we even untangle those questions? Here we've chosen sometimes to untangle and sometimes to not to untangle the problem. Yeah, but it is an interesting question. Clearly, that what I've shown you is only the beginning, I think, of a longer journey when it comes to causal forecasting. Stefan has done some work, of course, on in practice. I'm not sure if you actually ever published on this, and it's very important for promotional planning. There are a couple of papers I found just this morning. Causal transformers for in a medical scenario. This is from LMU in Munich. Rob Hindman is starting to get interested. Always a good sign, And there's the Van der Schaar lab in Cambridge that also has a lot of work on deep causal learning. So I think this is clearly an important topic that will get more traction. What I try to show you here, where the first steps in this direction, and we'll need a lot more steps. And with this, I want to thank you for your attention. Now there's stay connected on social media, or there's also a course I'm running. Thank you very much.
Thank you, Tim, for a wonderful and very interesting talk. We have lots of time for lots of questions, so let's start up front.
Thanks for amazing talk. Can you comment a bit on the? So you mentioned about the inventory you have, is that like it's a bit different because basically you have to always redistribute, right? Like there's a fixed inventory. Can you maybe just comment like how the inventory comes to hold this demand forecast? Because like if the inventory level is low, like you shouldn't the demand forecast you do, if you don't include that, then it will be wrong, right?
You want to be at the end of the season. You want to be at zero, right? That's so the pricing is it's an inventory management mechanism.
I see. Like you have let's say whatever inventory at the beginning of season, you wanna get to zero.
Yeah.
I see.
But then the question of regional redistribution that you're asking, that is also very interesting. I totally ignored it here. The demand. So Zalando has a fulfillment network of considerable size, but the demand may manifest in a place in Europe that is very far from where the actual inventory sits. Right now, Zalando is always fulfilled it across Europe. It works with because we don't have any borders. It doesn't work as well in the UK anymore, for example. But how do we then sort of redistribute optimally? That's a question that's completely ignored here. But there are other teams in logistics that think about this.
First of all, great presentation. Thank you very much. Learned a lot. I'm trying to understand a little bit more what you exactly did. Then my understanding is that this is a kind of forecast optimization. Like you're using deep learning not only just to forecast, but also optimize what your decision through that forecasting scheme. Then you're using causal variables like price, and I think that's the only causal variable that you're using it.
Yeah.
Is that correct? Then, that's rational that in forecasting you are using the variable that you have control on to make prediction and optimize that. But do you think if we look into other causal effects that you do not have control of, it's better, or you just keep on correlating effects to optimize your forecast.
Maybe a couple of clarifications. So we separate out prediction and decision making. So there's this forecast and optimize paradigm, and I think that's the way you should do it, unless you do reinforcement learning. So maybe that as a clarification. There are more causal parameters at play, primarily marketing, right? And you want to my sister organization is actually doing marketing, right? And then you have the question, should I be spending more money on TikTok, or Facebook advertisements, or is it a better investment to lower the price? Or probably you want to do both at the same time, something like this, right? So that's a very, very important causal connection that we're not making at all. And we should be making it, but we're a couple of steps. That's a couple of steps ahead of us at the moment.
I'm curious about the state of things before you arrived. Obviously, you contributed so much. And when you started your talk, you said, I've been working on bringing the effects of price into the forecasting. So was there no, were they just forecasting by ignoring the price previously, or were they using less sophisticated models? Or I'm just quite curious about the state.
Yeah, so actually the most important thing was that that I made this as a sort of a central artifact, the sort of elasticities that we needed to control. So we weren't able, for example, to compare elasticities from a classical econ approach to the kind of elasticity as our transformer gave us. And I thought that this was a negligence. What's the word? Yeah, that we needed to fix. So sort of, it was a bit of a mindset change at first, and then changing the models accordingly. So making sure that we're monotone and those things. And it's not just throwing our hands up in the air and hoping for the best. So and then
I was also a bit curious on the graph with the discounts. Mm-hmm. It's monotonically going up and to the right, but it's not monotonic in the first derivative.
Yeah.
Any intuition around why my elasticity is going to shift as the discount? I'm going to be more sensitive at some ranges and less at others, and then it's going to go back the other way.
Yeah, so I mean that's the kind of question an economist would ask me all the time. And I would say, yeah, but it's what the data tells us. So why should you make a structural assumption apart from monotonicity? I would ask back. It's for me, it's not clear at all, right? So I can totally see that in some regimes it's flatter and some it isn't. But ideally, I'd like this to be flexibly learned.
Yeah, actually, I have two technical questions. So the first one, on the results of your first experiment, you had the light GPM there as well. I was wondering, did you somehow incorporate the monotonicity there, or it's just structurally you?
No, actually, I think there is a way to.
How can you incorporate
light GBM? You can make your features monotonically depend on price. So we did that.
So you use this feature of light GPM to incorporate. And the second one is on the data for using the transformer. You mentioned that you should have some regularity or conformity for actually training a transformer, not just data size. So any advice on that? How to measure that? Should you have correlated times with correlated features? No. Okay.
Yeah. Well, we tried to come up with a couple of things, but nothing convincing.
Okay, that makes sense.
Yeah. So most of the work was centered around self-price elasticities, right? And there was a lot of effort in the 90s and 80s by economists trying to build complete demand systems where they would also consider the cross price elasticities. Because at the end of the day, the most important thing about prices are relative prices rather than the absolute prices, right? Is there a plan to work towards like this gross price elasticities and a vector autoregressive approach to all of these?
So yes to the former, second, no to the latter question. I think cross price elasticities are totally important, but it's a different order of magnitude. It's like an order of magnitude less. You can try to estimate it, and we're working on it. It's actually most important in the setup of A/B tests. So it doesn't have to do anything at all with elasticities, but you want to make sure that if you just randomly split your products into group A and B, and then you run an AA test, you typically see an effect even though you haven't tested anything, and that has to do with the fact that you have cannibalization, all of these correlations. And in A/B tests, you need to absolutely account for it. In the price elasticities, I think we have at the moment we have bigger fish to fry than this. I would, for example, much prefer to go to a probabilistic model first before we go multivariate. One of the problems I brushed under the carpet here is that every price change we make has a cost. And because of this display change that I showed you at the beginning, we need to be very, very careful that we don't make too many, or we should be careful about not making too many price changes. So I would go probabilistic first, and then work on multivariate approaches. And that, Chris, is also something like where it pains me every day that in 18 months we haven't had probabilistic forecasts yet at Zalando. Yeah.
Let's go ahead over there.
Yeah, so you've brought up a couple issues of other causal effects like competitors, marketing. How do you judge the scale of the effects on the internal platform display, like as a result of search? I mean, for example, does the search order a function of price or discount? And you can get a bit of a feedback loop with that.
Yeah, I think it's. I would essentially repeat the answer I gave here was totally a problem, right? The position in your search results really has such a big influence on demand, and then also price then influences where you end up in search. But we're ignoring that for the moment.
That's a bit of a chicken-egg problem, right? Because you'd need to forecast who is going to search for something, for what are they going to search, what's their sales history, because that's going to have an impact on what they see as a result of their search. So there's a lot of biting your own tail, I think, in there. An interesting question. All right. So many people. Let's start at the back.
Okay. While estimating the relationship between the demand and price, do you consider the effect of the special days, for example, Christmas, for example?
Yeah. So I didn't have I think I had a slide on the covariates that we include in the model, and then special days are totally a part of it, right? You need to know where is it? You need to know about. I can't find it. You need to know about the special days, but and also when a sales event period starts. But somehow it's also incorporated in the price, right? So typically on those special days, the prices will change quite a bit. Calendar effects are totally covariate.
But not only when you are forecasting, but also when you are doing the decision making, do you differentiate your strategy when you are in different periods?
That's not true. So, I mean, I already talked about sales periods and non-sales periods. So there's a bit of a high-low pricing strategy, right? And then the decision problem that I showed you here is for the non-sales period, right? For the sales period, you do have you update prices more frequently. In Cyber Week, I don't know, hourly or something. So there's a different price engine for the sales periods, or different. Let me be more careful. A differently parameterized price engine.
Thanks for your talk. I was wondering, you talked about that you retrain the model every week. And I can imagine, also from experience, that these elasticity curves can vary wildly from week to week or day to day. So what kind of checks or monitoring do you do to make sure that the model is kind of robust? I can imagine if you look at like a forecast metrics overall that it will stay roughly the same, but does it still make sense if you would look at the elasticity curves week over week for all these products?
Yeah. So we compare elasticities against sort of a two-way fixed effect elasticity, and then we have, if they go outside a certain range, we have an alarm and someone needs to go look at it. So that exists. We also have used the last K models, and then we let them run on historical data or just observed data, so that we get a handle on how much did the performance change, accuracy change with every retraining. So there are some checks and balances. And they don't jump around as much as we would fear. So yes, please.
In the second method out of the three, which is the combining of the causal and baseline forecast, did you remove the price change effect in the forecast?
No, but that's a great observation. Hang on, where is it? I said that this year is the base demand. Where's my cursor here? This year is the base demand, but it really isn't, right? We should factor out. We should essentially use the price elasticities here to go back to the sort of black price, right? We don't do it here. We could. Yeah, it's a good observation.
Yeah, do you have any idea in mind that it could be a good way to remove that in the baseline?
It's something that is on our to-do list. It should make a difference, But I mean, one thing I brushed under the carpet here is that this epsilon here, if we estimate it with a two-way fixed effect model, and we make this sort of exponential assumption, you need to be very careful, right? Exponential growth doesn't continue forever. The functional form of the two-way fixed effect model, where is it? That's of course wrong, right? It should be some S-curve shape. So you also need to be a bit careful that you're only using this epsilon within sort of 20%, 25% price changes. Otherwise, all hell breaks loose.
If I understand correctly, you also tried some data augmentation approach by creating an additional training data using the elasticities, and that didn't work out as well as you would have hoped. Do you have any intuition about why that might be the case?
No, and that's a painful thing. So we were. We were trying to tease it out. Essentially, first was basically what's the kind of effect that we wanted to equip the transformer model to learn better. And I thought, okay, that would be the extreme price changes. But then, if you choose those, if you're in the regime where you're worst for the extreme price changes, it's not such a good idea. And then we went to the smaller price changes, and there, I can only speculate, but we didn't see a big improvement, and potentially because we had enough historical evidence of that, unfortunately. But I think it's still such a simple idea; it should work.
let's have perhaps one last question or two last questions before we go to lunch because everybody's hungry.
I'm wondering, does the model take into account that if like a discount lasts for a longer time, that the effects per period will be smaller? Like this kind of...
No. Should it? Yes.
I don't know if it's like a very small effect, maybe it should.
Yeah, that's a very interesting thing, right? You have, if you think about this discount grid, right? The object of interest, I was saying that we needed to be a tensor, right? Of 3 dimensions. Where is it? This one. Oops, this one here, where the third dimension is, for every discount level, you have a probability distribution of what the demand is. And what you're saying is we should have a 4th dimension, where, and you're totally right. But that's a kind of multivariate, then you would have sort of a multivariate distribution conditioned on the price, multivariate in time conditioned on the discount level, and yeah, that would be it's something I haven't thought about. So.
Yeah, but it's also about step after that actually. So if you then do you want to find like an optimal promotion plan to maybe by not taking this into account that you get like maybe an unrealistic plan or something.
Yeah. The bigger simplification we make actually is in the optimization problem where we essentially at every stage. So we set the prices optimally for the first week, and then for the rest of the time we assume that the prices are always set in an optimal way. But that clearly will not be the case, especially if you're in a high-low regime, where your pricing may be artificially too high during certain periods. So what I would do first is to potentially try to predict price, to have a most likely price in the future. And then have a more realistic optimization problem. So the question is great, but there's more groundwork to be done first.
Perhaps one last question.
You mentioned a couple of times that model or the decision-making part of it. Do you have any comments how that would be? Are you thinking of implementing something like that?
So no, and the Amazon folks, they tried for inventory management. I think about 3 to 5% of their Amazon inventory is controlled by a deep reinforcement learning inventory management system. But they're, to the best of my knowledge, at least 18 months ago, they weren't able to roll it out. There's a lot of all of these intermediate artifacts, that we produce when we do this forecast then predict. When we follow that paradigm, they give a lot of control, and that is much better than having a deep learning, even if it's a deep causal learning black box that does something, right? And if it's sort of mission critical to the company, it might be much better to be a bit more transparent in terms of modeling. It's also our job guarantee. So.
All right. So thank you, Tim, for a wonderful talk.
Michael and hey, hello. I want to thank you for your foresight. And then for Yep.
I look forward to it.
We'll see you here.
They don't ever do it. And the other question, the second one, we will have to discuss.
Yeah.
So, do you have questions in the ISF? Du musst Amazon Causal
Mache ich das. Nichts darüber schreiben, was wir machen. Nichts darüber schreiben, was wir machen. Das willst du nämlich auch nicht lesen. Diagnose und wie das dann nachher zu einer Optimierung wird. Das sind so Sachen, die
Okay. Maybe I don't get that part entirely yet.
Of course.
I feel like
take care of the assumption of that the procedure has to be zero value.
Yeah, indeed.
Zero as the value of the incentive.
In the double ML,
Yeah.
no. So
Do we have to say that?
no, that's an assumption you make before. In a sense, I mean, we don't follow the double ML methodology gives you is a causal inference technique, and we only use it for inspiration point purposes, essentially. So if you're the fact that you don't have a bias in the model, all models, you unfortunately have a bias in the wrong direction. So no, that's a good question.
I see. Bias is also very much key. Because of like substitutional, especially for substitutional group, we don't want to. Thank you, yeah, for answering. And it's a great and very inspirational for the students.
I was with this econometric / machine learning based approach with the exponential smoothing of effect of price. In this ratio, I was thinking that it's almost like it's a relative price versus what happened in the past.
Yeah, exactly.
And the idea I had is what if the price in the denominator is the price in the
Yeah, if we can anonymize it in some way, I guess that would be the best. Then it would still be possible, I guess. And I can say